Hello.
Hi. Hi, Kenneth.
Hi, James.
Hey, how are you?
Good, thank you.
What's up?
Uh,
I have made you presenter, so you should be able to test your screen, share
okay.
screen. Yeah.
Let me try share that one.
Got that.
And then if I do this, are you seeing the
Yes, perfect.
right thing?
Yes.
Yeah. And if I move my mouse, that's visible.
I can't see yes, it is. It's just
Okay.
tiny. Yeah.
Yeah.
Okay.
Okay.
Cool.
Okay. Right. I'll stop just while people join, and then I'll share again now that we know it works.
All right, thank you. Yeah, we'll just wait a moment for others to join, then we can start. But in the meantime, I can tell you that well, of course, welcome to our group seminar, and thanks for offering to give a talk. I'll just give you an overview of what the demographics of our group is. We've got a mixed group of many faculty members and also a lot of students and postdocs. Some of us do galactic science, some in the group also do extragalactic science. A huge fraction do radio astronomy. We have people doing machine learning as well. So maybe those information will be helpful for you to keep some of the explanation to a level that everyone will be able to pick up.
Yeah, I think I've got quite a good kind of scientific background that I think should be reasonably accessible. I've done this talk 3 times now, so I think it should be well practiced, well
Okay.
timed, and there's at least the good third is a kind of a nice historical background, and then it will get more technical at the end, but I think still at least with understandable outcomes and things. So I think content
All right,
should be good.
okay. That's good. Thanks, Kenneth. I would just give another 2 to 3 minutes for people to hop in, and then I'll ask Willis to introduce you, and then you can go ahead and share screen and start. All right, thanks a lot. Can I answer? Hi, Willis. You can now go ahead and introduce Kenneth. Good afternoon, everyone, and welcome to this week's seminar. This week we have Kenneth Duncan, and Willis will introduce him, and then we can get going. Thanks, Kenneth, again for accepting to speak to us.
Thank you very much, Prof, for the opportunity. So today our speaker for the seminar is Dr. Kenneth Duncan, who is an Ernest Rutherford Fellow at the Institute of Astronomy, the University of Edinburgh. Dr. Kenneth Duncan is an extragalactic observational astronomer, currently based at the Institute for Astronomy, as I've said, where he holds an STFC, Ernest Rutherford Fellowship. His research explores the early formation of galaxies and the coevolution of galaxies and supermassive black holes at high redshift, with a particular emphasis on combining next-generation radio observations with deep multi-wavelength photometric and spectroscopic surveys. Dr. Duncan holds a leading role in several major international observing collaborations and contributes to a wide range of projects spanning the electromagnetic spectrum. He earned his PhD in astrophysics from the University of Nottingham under the supervision of Professor Chris Consellis, with a thesis titled The Growth of Fast Galaxies. He also holds an MPhil in physics from Durham University. Prior to his current role, Kenneth held research fellowship at the Leiden University and the University of Edinburgh, including positions as a Marie Curie Fellowship and a Leiden Edinburgh Astronomy Fellow. Thanks very much, Ken, for accepting to give us this talk, and you're welcome.
Thank you for the introduction. And yeah, I still can't say Marie Sklodowska, I think is the correct pronunciation. But yeah, my Polish is not it's not strong. So yeah, I think here we go. You should be able to see everything now. And yeah, unless I hear that you can't see anything, I'll make a start.
Yeah, we can
So yeah.
see your screen.
Perfect. Thank you. So yeah, thank you very much for the invitation, and yeah, really pleased to share some of the results that we've had from our work, but also maybe some forward look into some of the exciting things that we can still do in the future with new radio surveys. So, as I mentioned, I'm based at the University of Edinburgh with an Ernest Rutherford Fellowship funded by the STFC, which is part of the UK funding agency. And my work spans a range of different multi-wavelength kind of surveys. And the kind of key ones I'll talk about today are sort of illustrated here, and I'll come back to these later on. So the talk is split into sort of three parts. The first of which I'll try and give you a nice overview of high redshift radio galaxies. What do I mean by that? Why are they important? What's the historical background? As well as some more recent results on this topic, before I move on to talking about some of the first studies of these types of sources with the James Webb Space Telescope. And then finally, I'll move on to the sort of future prospects with an optical survey that I'm leading that is targeting a large number of radio sources. So to start, I'll talk about the background. So I like to start with this image, and I'm sure most of you, if not all of you, have seen this image from the Event Horizon Telescope. So this is looking at the surroundings of supermassive black hole at the center of M87 with the Event Horizon Telescope, and to me is one of the sort of best technical and scientific achievements we've had in the last decade, I would say, because it really gives us irrefutable proof that at the center of nearby galaxies, and now including our own with the later results, we have these supermassive black holes, and the geometry of this image can directly get a mass estimate that really robustly tells us that this is a 6.5 billion solar mass supermassive black hole. And while that's fantastic and confirms a lot of our previous theories and estimates of these masses, to me, one of the interesting questions that this points to is the fact that we don't really understand how it got to be that big. It's 6.5 billion solar masses now, but when did it grow to be that big? How did it grow to be that big is really not well understood. So it's one of the main questions I'll be talking about, is that sort of the bigger theme in a lot of extragalactic research is, how do supermassive black holes form, and how is their growth coupled to the evolution of their host galaxies? So again, I'm sure most of you have seen a similar picture of this. We can trace how active black holes are growing based on when they're accreting. So we have our broad picture of accretion around black holes, where we have an accretion disk surrounded by a torus of gas and dust. Some of these are also then producing these extended relativistic radio jets. But between X-rays tracing hot gas in the corona above the accretion disk, through to UV and optical continuum of the accretion disk itself, narrow line and broad line regions looking at the gas around these regions, and then the torus and the jets, we've been able to build a quite comprehensive picture of a lot of aspects of how black holes have grown. And one of the things that has shown us, and one of the interesting questions one of the interesting things we've found that opens up new questions, is this picture that the most extreme, the most massive black holes seem to have had kind of most of their activity and have had their growth the earliest in the universe. So you can see that shown with some X-ray observations. So this is data taken from the work by Miyagi, looking at the space density of X-ray sources over cosmic time, split by different luminosities. And in this case, the luminosity, the X-ray luminosity, is telling you, scaling with how big and how much activity is going on with that black hole. And you can see that as you go from the black, which is the weakest and the lowest mass black holes, down to the orange, which are the most kind of massive, the peak in where their activity is maximum moves to earlier and earlier in cosmic time. So you can see the peaks shifting. And in fact, if we look at this first, just very early period of cosmic history, there are now hundreds of supermassive black holes detected from optical quasars mainly, with estimated stellar masses, or black hole stellar masses, up to 10 to the 10, and certainly in the billions of solar masses as a black hole mass. And you can see relative to M87 in our local neighborhood, right? These are building things as big as M87 is built, but doing it within the first 5% of the universe. And you can see again, many of these are hundreds to thousands of times bigger than the Milky Way's supermassive black hole is now, but they did it within the first billion years of the universe. Even some of these very extreme ones that are just really pushing the limits of our theory. And you can see for sort of traditional pictures of how we thought black holes grew, this gray line shows the theoretical kind of upper limit of end in limited accretion. And while most of them are below, there are a few of these sources that are really pushing the limits of what our theories were doing. So this is telling us that not only did kind of overall activity peak early in the universe, the most extreme ones, the most interesting ones, peaked very early. And what's not shown here is some of the new results from recent JWST studies, finding many more of these lower mass but still interesting, potentially challenging supermassive black holes that are even higher redshift but lower mass. So we have this picture that activity seems to have peaked early in the universe, but there are a few challenges associated with this. So the first of these is that other studies with X-ray observations over cosmic history have built up this picture that actually between 60 and in some studies over 90% of black hole accretion is obscured to us. So we're not actually seeing the bulk of the actual growth of these black holes. It's obscured by gas and dust within the surrounding the black hole and within the galaxy itself. So when we see these very extreme sources that I showed before, so these ones on the right, this is really just a small subset of these overall this overall population. So in terms of trying to understand how black holes are growing, right, we're not actually observing a huge fraction of it. The other challenge comes from the fact that these black holes that we do know about are typically seen in quasars. So this is where we have a relatively unobscured view of the accretion disk surrounding the supermassive black hole, which is great because it allows us to see these out to cosmological distances. But the difficulty is that optical emission blinds the light we can see from the host galaxy. So to illustrate this is a simulation from before JWST of what one of these high redshift quasars would look like in James Webb. And you can see in the left-hand image, this is the sort of the raw emission that you'd see, which has got this very bright point source. And if you understand your point spread function, you can just about subtract it and see the faint fuzzy galaxy left behind. But this relies on, firstly, lots of data. So these are long James Webb exposures with a very expensive and difficult instrument. And even when you do it, there's big uncertainties and there's difficulties where if you don't quite get your point spread function measured correctly, you can completely get the measurement wrong. So this has been shown to work with JWST, but it's very difficult, it's very time consuming. And even once you've done it, you're still not seeing very much about where that black hole lives. Right? You're getting a very limited picture of that galaxy. So in terms of the key questions I brought up before, right? How do supermassive black holes form? Well, we can't tell properly because we're not seeing all of that formation. We're just seeing a small subset of that. And then the second question of how that growth is coupled to the evolution of the galaxies themselves, again, we can't really answer that with these samples because we can't see the host galaxy they live in. And this is where I argue that radio observations start to come in. So I think, yeah, many of you will know, even if you're not working on kind of extragalactic fields, the power of radio for other traces. We have primarily radio continuum, so this is driven largely by synchrotron emission. And this is great for studying distant galaxies because it gives us an obscuration-free tracer of AGN activity and star formation. So because we're looking at centimeter to meter wavelengths, the small dust grains are not impacting that. With the sensitivity of LOFAR and Meerkat, even star formation now out to really kind of huge cosmological different distances is very easy to measure. Alongside the continuum emission, we can also start to measure things like polarization, which is a really unique probe of magnetic fields within the galaxies, but also the AGN and the wider large-scale structure. And then, particularly with the power of Meerkat, right, the ability to do spectral line studies is rapidly improving. So atomic gas H1 gives us gas masses and gas fractions, as well as the kinematics of that gas. But also then for star formation in galaxies, the masers that we can pick out potentially probe these sites of the most extreme star formation. So radio is potentially really powerful, and actually has had a very long lived role in the study of the objects I'm talking about. So bringing in some more of the history, our first real discovery of these distant quasars was led by radio. So in terms of the history, this early radio catalogs from the third Cambridge catalogue of radio sources, Martin Schmidt, in following up one of these sources, so the famous 3C273 kind of radio loud quasar, this was confirmed to be a redshift 0.158 by Martin Schmidt, and this was at a point where redshifts being probed were very, very local. So this is properly moving out to the distant universe for the first time. And over the following kind of decade, there were lots more of these bright radio sources followed up with optical telescopes and increasingly powerful and large optical telescopes that were able to push the study of these bright radio sources all the way out to redshift 1. So this was the frontier of our understanding. Radio was the way that we were able to pick out these objects. And a lot of this work was pioneered by Higher and Spinrad, using the 200-inch Hale telescope that you can see on the right in California. And you can see an example of one of these distant sources, a redshift 0.75, which doesn't feel very high now, but is actually going back a large fraction of cosmic history. And although this looks like a potentially quite low signal noise spectra compared to what we can do now, these objects have been subsequently confirmed, and a lot of this pioneering work was the way we could push the records further and further. So I would say, kind of looking back at the history, the real peak of activity of using radio to do this was probably in the 1990s. And this was built on combining a couple of different empirical observational relations. So the first of these was the Z alpha relation. And this was an empirical correlation between the redshift of the objects they'd found and the spectral slope in their radio. So the synchrotron emission is given by this, can be modeled quite easily by a sort of simple power law. But as you go to higher redshift, the energy losses from inverse Compton from the CMB background scale as 1 plus Z to the 4. So the more energetic photons start to lose their energy quicker, you lose the higher frequency emission. And this led to the sort of the idea that if you look for steep spectrum sources, those are going to be preferentially at higher redshifts because the higher energy photons have been killed quicker. And as this is working, you can see here empirically, right, just the redshift of the sources versus the spectral index. If you were to limit to only the steepest spectral index things, you're limiting yourselves to generally redshift 1 and above, whereas if you just took everything, most of the sources are down here at kind of redshift 0 to 1. The other correlation that was really powerful was this KZ relation. And this, again, is very empirical, just linking the idea that the radio galaxies appear to live in generally very massive galaxies, and the K-band optical near-infrared magnitude is basically tracing the amount of stellar mass. So if these all live in the same galaxies, if the K-band magnitude is fainter, then the galaxy is going to be typically further away. And you can see this sort of empirical correlation of the radio galaxies where they live in a kind of relatively tight correlated band. So if you look at things that are faint, they're going to be typically higher redshift. And this really worked, and you can see the examples on the left still, right? That a lot of these were picked out based on combining deep spectrum and the K-band magnitude. And this led to, what at the time in the late 90s was this most distant galaxy discovered, so pushing back to redshift 5.2 now. This was, again, still pushing the boundaries of what our discovery space was in terms of distant galaxies. And this was a great time. I'll move on to some of the other things that we learned from these, but in terms of that ability to push out to kind of unknown territory, after the 1990s, it probably was the end of the golden age for radio, because you had things like the Hubble Space Telescope doing the very deep kind of blind surveys, so Hubble Ultra-Deep Field, where within these images you can start to pick out normal galaxies out to redshift 4, redshift 6 in big statistics, and then simultaneously these wide area optical and spectroscopic surveys like SDSS were starting to find just regular optical quasars without radio pre-selection, all the way out to redshift 6 and starting to probe into the epoch of revaluation. So it's not that radio stopped being important, but in terms of really pushing the regime and building these big and completely new novel samples, I think a lot of the effort went into different data sets, and really I think the radio became a little bit more of a specific tool for studying the subpopulations. But one of the pictures that did build up over time was that these high-redshift radio galaxies are really important laboratories for studying kind of galaxy evolution as a whole. So I mentioned that these radio sources were found to be in the most massive galaxies. And this means that they're also then probing the most massive dark matter halos, and in many cases also being tracers of protoclusters and kind of the earliest forming large-scale structure. And you can see one of the classic examples here on the right is the Spiderweb galaxy. It's a very luminous radio galaxy, redshift 2.2, but it lives at the center of this very extreme kind of overdensity that is likely to evolve into a very massive cluster by redshift 0. Another key factor that's become important in broader galaxy evolution is this idea that radio mode feedback, so the energy dumped into the galaxy by these jets, is a really critical ingredient in shaping the galaxy stellar mass function across galaxy simulations. But a lot of the details are still very poorly understood. The way we link the accretion to the feedback is based on some very simple prescriptions that still need kind of to be probably worked out. So if we want to actually answer these questions, right, we need bigger samples of these high redshift radio galaxies out to higher redshifts and across broader parameter space in order to start answering these questions. And if we do that, then we have very unique populations to constrain not just supermassive black hole growth, but also broader galaxy evolution. So that brings us a little bit up to more nearby kind of data. And a lot of the work I've been doing in the last few last 10 years now is with the low frequency array based in the Netherlands. So as was mentioned, I moved from Nottingham, where most of my work had been on Hubble and kind of very deep fields, to working with the radio teams based in Leiden. LOFAR itself, for those that don't know, is based in the northeast of the Netherlands, but has international stations that extend all the way out to now Bulgaria in the southeast and Ireland in the west. So it has 1,500 kilometer plus baselines that allow the prospect of extremely high spatial resolution. Most of the results I'll show, however, are based on just these sort of Dutch stations, which is where the wide area imaging is most kind of sensitive and efficient with LOFAR, which gives you a resolution at 1.2 144 megahertz of about 6 arc seconds per beam. Just to illustrate, the core here is this is the super turp based at the very core near Twingalo. And it took a long time to get up and running. Analyzing the new data, dealing with ionospheric corrections was difficult. This was stuff I had no direct involvement in, so don't ask me the details, but people like Tim Shimwell at now Astron were leading the reduction. And after a few years and burning up time, we were able to produce the LOFAR 2-meter sky survey, which is now, as I'll show, kind of nearly complete over the Northern Hemisphere. A lot of the work we've been doing is based on LOTS DR2. So in terms of overall statistics, it's approximately it's 10 times deeper sensitivity compared to FIRST in terms of the effective sensitivity, which corresponds to about 100 microjansky per beam, kind of RMS at 150 megahertz. And the previous comparable kind of deep survey at this frequency was the TGSS using the GMRT that was 2 to 3 millijansky. And the kind of the main survey main data release that a lot of this worked on was LOTS DR2. So DR1 was just this small area in kind of light green. DR2, however, covered 5,500 square degrees. And crucially, alongside the radio, we put in a lot of effort to making this scientifically usable. So this included generating optical IDs for the sources, using a combination of statistical methods, but also big citizen science programs to associate radio components, augmented with different machine learning approaches as well. And then these were then coupled with work that I did building all sky photometric redshift catalogs in order to make these data usable. So yeah, the radio data alone is great, but we need redshifts and host galaxy properties. Alongside the wide area coverage, we've had a lot of work going into these deep fields as well, which targeted a few smaller patches of sky. So 3 or 4 of the kind of the best studied fields in the Northern Hemisphere, covering about 10 square degrees each. And this has given us very extremely deep radio continuum, so over 50 square degree. And that's 10 times greater volume than the previous surveys like the VLA 3 gigahertz survey, and is still is comparable to the confusion limit for MeerKAT with surveys like MIGHTY, but over a slightly larger area. And again, like with the wide area survey, we put a lot of effort to producing not just the radio, but also the multi-wavelength data to make these useful, photometric redshift, source classifications. And this has enabled a lot of studies across cosmic history. So I'll point you to surveys or papers like the Best et al. 2023 for the source classifications, or Rachel Cochrane's work on looking at star formation over cosmic time with the radio population. To bring you up, kind of fully up to date as to where we are with LOTS as of last month, so you can see the date this was taken. I don't think it's changed since then. What will become LOTS DR3 for public release, hopefully later this year, now covers almost all of the Northern Hemisphere. And certainly all of the extragalactic sky in the Northern Hemisphere is now fully covered. So this is 47% of the sky. And the radio catalog corresponds to now 13.7 million sources, which is over 10 times more than the biggest catalogs from VLA. So I mentioned the radio data should be public later this year, but the cross IDs and other things will follow later. So that's kind of where we got to with the data. One of the things that we were doing with that data as it came along was trying to go back to seeing how far could we push the sort of the most distant supermassive black hole studies by bringing in radio and using that as a means of improving our survey selection. So this is work that was led by a PhD student that I worked with, Annie Cloudermans, who was at Leiden Observatory, is now a NOIR Lab fellow out in Hawaii. And the idea here was to combine the optical data with radio to see if we could find new populations of radio loud quasars. So the starting point was my photometric redshifts that I mentioned before, these all sky photoz's. and just requiring a kind of very loose hierarchy criteria, so much less conservative than other previous approaches have taken, but also then requiring that there was a detection in the radio on the basis that the biggest contamination for the optical searches is usually brown dwarf stars, which at the time we thought shouldn't be showing up in radio. Although we've now found actually there are some populations of these brown dwarfs that do have these radio flares that show up, which is astrophysically interesting, but does still contaminate our searches. And in the end, we got to 142 of the candidates from all of the 5,700 square degrees of lots DR2. And we're able to get telescope time to follow up 80 of these. And crucially, the good news is that we were able to confirm a large fraction of these. So you can see just a nice visual representation of the redshifts. So going from lowest to highest redshift in this sample. So we had 24 that were detected or confirmed out of the 80, which again might not sound like much to people in terms of numbers, but this is actually double the number of radio loud QSOs above redshift 5, right? So even though it's a small number, in terms of this population, we were kind of already producing really novel contributions to these samples. I think what's particularly interesting with these is that the radio data is now sensitive enough that when we say this is radio detected, radio loud is maybe not the right terminology to use anymore, because if you look at these sources, so radio loudness here is basically a sort of metric of the relative luminosity of the radio to the rest frame optical. And in this metric, people would say everything above R equals 10, we would define as radio loud. Anything below this is faint, and you can radio quiet. And you can see that actually many of these things are kind of on the borderline. So we're detecting things that are kind of technically radio quiet, but still showing up in the radio. And I won't talk about it more, but I'll advertise work done by a student here with me and Philip Best at Edinburgh, Bohan Nui, who's produced papers looking at this in a lot more kind of detail to really update and modernize our definition of what we call radio loud or radio quiet quasars. But you can see these span redshift 5 all the way up to kind of redshift 6.5, so really early into the universe. But some of the ones we've picked out have got very high radio loudness from very extreme sources, but also things that are kind of relatively radio faint. If we look at the optical properties versus the radio, so M1450 is the rest frame UV absolute magnitude. And if we compare that to their radio luminosity, you can see that in this case, so left hand here is brighter, fainter things are on the right hand side in the UV. The population we're seeing are things that are fainter in the UV, so in the rest frame optical and infrared. Sorry, in the observed frame optical and infrared. These are fainter than the quasars that people have discovered before, but actually in some cases still much brighter, much more luminous in radio. So these things, even though they're faint in their optical, are actually potentially quite extreme in the radio and doing very interesting things when it comes to feedback and that kind of early movement of baryons around the universe. So this work by Anik really demonstrated that if we include the radio, we can really improve our ability to detect these faint high Z quasars. And we had a 34% success rate, which might not sound like high success rate, but many of these optical only studies, their success rate is more like 1 to 10%. Right? So we can find these things much more cleanly. And again, one of the interesting things that we're seeing is that these might be faint optically, but they are extreme in the radio. And one of them in particular, so this source down here, which is lower redshift than we were intending, so redshift 4.9, is very extreme in the radio. Meant it was very bright enough that we could start to go back and use all of the international stations from LOFAR. So this is work that just came out earlier this year. We had a nice press release. So I mentioned most of the work so far was just using the Dutch stations, and you can see the low resolution. There's a kind of radio blob, but maybe there's other source that kind of could be associated with it. but the main bright blob is kind of sits on top of this red optical source. When reprocessing the data, but using all of the international stations, you can get down to sub-arc second, so about 0.3 arc second resolution. You can now start to see the extended structure where you have this sort of clear jet being resolved north of this source, and still seeing the sort of fainter lobe to the south. And to show you the kind of the more sort of science kind of focused plot rather than the press release image, you can see the direct line. You can see now the core of the radio source on top of the galaxy lining up directly. So you have strong confidence that this other lobe is associated. It also has a relatively good match in spectral index, which is what we'd expect if they were the same type of source. And crucially, this is at a minimum, if you just calculate the size of this jet, this has to be at least 66 kiloparsecs in scale. And why this is particularly interesting is because I mentioned before that the inverse Compton increases as he goes 1 plus z to the 4. The thought was that these very extended radio jets shouldn't exist this early in the universe because they should be being kind of killed off by the inverse Compton. But this is at least 66, if not more like 100 kiloparsecs, depending on the orientation. And you can see where this sits relative to other populations that were known. So these other high redshift things that had a size measurement, right? They're all very, very small. The one we've found is of order 20 plus times larger than any previous jet at this redshift. And much more comparable to sources down here. And even though redshift 4 to 5 might not sound like a huge difference, right? That's if you say that redshift 1 plus z to the power of 4, that's a huge difference in the energy losses that should be kind of pushing this source down here. And again, while these are extreme in the radio, they're relatively kind of normal and faint and potentially actually quite kind of low luminosity kind of quasars compared to the rest of the population that have been discovered so far. So again, showing kind of putting this in context, this source is the star down here. We have follow-up spectroscopy to get estimates of the black hole mass, and we can look at where it sits in this parameter space, and it's relatively low in terms of its black hole mass compared to these other sources, much more comparable to lower redshift sources in SDSS. So we're still looking at a very extreme source here, right? But we're starting to get into kind of the more normal population, but able to do this now at redshift 5. So this is interesting, right? But we're still looking really at mainly things that are kind of quasars and not just radio-only detections. What we think is still out there is a huge population of these sources that have yet to be discovered. So this is a plot that just shows the known kind of high-redshift radio galaxy and quasar samples as a function of redshift and their power. So this is older work that Anik did before we had the new discoveries of these were known quasars at the time. You can see that even though they're bright in radio, they're still orders of magnitude fainter than the most luminous, the most extreme radio sources. And there is this huge population kind of still to be discovered that are, much brighter in radio, but potentially fainter in optical. And we think, just based on estimates, that there could be 3,000 to 4,000 of these in lots, but also 30,000+ of these in southern hemisphere surveys like EMU with ASCAP. So there's this hidden population out there, but still need to be identified. And the radio surveys have really, I think, taken back over as the ability to discover some of these new populations. But we do need to go back and find them and to learn more about them. So we'll come back to the kind of the bigger populations later on, but the next section I wanted to show some of the work I've been doing and collaborators on more detailed studies of once you found these radio sources, what can we learn with new instruments? So this is looking at some of the first JWST studies of these high-resolution radio AGN. So I'll introduce this source. So like many things, it's got this very unformative telephone number named TNJ 1338, 1942. But this has been a well-studied source. It's one of maybe kind of the most prototypical of these high-redshift galaxies. So it's extremely luminous. It's one of the brightest radio sources out there in the sky in terms of its luminosity. But it's also extremely bright in Lyman alpha emission, right? And which suggests that there's kind of a lot of activity going on. And you can see that in the kind of green here in this HSD image. But one of the key things about the source as well is that it lives at the heart of a very significant overdensity. So there's this extended protocluster structure that it sits within that has at least 30 to 40 confirmed Lyman alpha emitters at the same redshift. So strong Lyman alpha emission that matches the redshift we see for the radio galaxy. But there's also potentially 60 plus of these just optical sources without Lyman alpha, but potentially with redshifts consistent with the protocluster. So it's one of these extreme kind of halos that might grow into a massive cluster at redshift 0. And there's also evidence with this Lyman alpha emission of AGN-driven outflows based on the structure, and I won't go into the detail, but there's a lot of work has gone into studying this source in the optical, which is probing the rest frame ultraviolet. So this is interesting. We could see there was some structure. I'll show now the HST. So this is Hubble imaging in optical, so 600 nanometers to about 850 nanometers. And this is probing rest frame ultraviolet, so 1216 angstroms Lyman alpha is in this band, and you can see some of this extended structure. And at the time, they thought maybe there's a kind of, you can kind of picture some kind of big disk edge on galaxy, and maybe there's an outflow of Lyman alpha, but it wasn't very clear. You can see there's not very much detail. You can't see much structure going on. There's no one region that looks bright to kind of confirm where the galaxy is. So this was the target that I led observations for in this Pearl's Guaranteed Time Observation Program led by Roger Windhorst. And it's a very short James Webb program, getting just 6 near-infrared to mid-infrared filters. So it's only 1,000 seconds of exposures, which is not very long for JWST. But when I reveal those images, you can start to see the power of JWST and what it can reveal in terms of the galaxy structure. So you can see now as you go to increasingly redder wavelengths, right, it's very clear where the main galaxy is. There's a very clear host down here in this region. And the emission up here that is aligned with the radio. So you can see now on the right-hand side, the radio contours of where this jet that's producing all this radio emission sits. Right, you can see that there's a very clear alignment between this extended emission and the jet, with the host and the supermassive black hole clearly kind of more down in this red host galaxy. And importantly, by design, we picked filters that had some of the key emission lines included. So this band has a lot of emission from the H alpha recombination line, similarly the O2 recombination line here. So you compare this to the 300, which should be mostly continuum emission, so mostly stellar emission. If you compare these two, you can see that where the nebular emission is coming from is all kind of dominated by this extended structure. So we can really easily see now that this jet is interacting with the ISM, producing this extreme emission. So to put this in a more quantitative fashion, if you look at the color, so I mentioned 300 to 335, where the color is the kind of the reddest, you can see that's where the strongest line emission is, and you can see that the strongest line emission very nicely lines up with where the radio peaks. So one of the questions, or a couple of the questions we had with this data we were trying to answer was, what is the nature of this jet-aligned optical emission? So, what is the jet doing, and how is that interacting with the galaxy? But also, what galaxy does it live in, right? To actually start putting into some context. And I will probably skip over some of the technical details, but we fitted both stellar population models and also some radiative shock models. And you don't need to worry about the exact details, but obviously feel free to ask me. We split this by different regions of the galaxy, so the core versus bits of the extended mission, and you can start to see the real difference in the overall spectral energy distributions. Down by the core, there's kind of very clear continuum emission. There's still bright emission lines that give you these kind of excess colors, but it's best fit by a kind of stellar population. This is mostly, we thought at the time, star formation driven emission lines. But as you go to the edge where the jet is interacting, the emission can only really be fit by these more extreme shock models where it's very, very strongly nebular emission dominated and very little kind of older stellar population going on. And to kind of color code this, you can see blue is regions that have a more complex sort of population that requires an older stellar population, kind of more like a galaxy. Yellow is these more extreme shock dominated regions, and the green is where it could be kind of just a very recent burst of star formation, perhaps driven by the jet. And we did explore whether this could be produced by AGN kind of photoionization, and it's a complicated plot, but I'll just pick out the key points. The color coding here corresponds to what you can see on the left. So each of these regions has got, if it's kind of yellow and green, it's sort of one of these ones. If it's purely green, it's one of these green points over here. And the blue, more complex models are down here. So you can just see in this color space, compared to different models where they lie. And actually, these extreme regions over here, which is kind of these models, regions over here, sit where the radiative shocks are, whereas the AGN models that we compared to were much more down here. So we thought maybe this is just driven purely by shocks and maybe some recent star formation driven by the jet. And then what would that mean for the galaxy if we take all of the emission and say, right, we believe all of it's from star formation and is the galaxy? We can get potentially up to a very massive, so 10 to the 11 solar masses in terms of the stellar mass. If you're more conservative and you say, right, I only believe the kind of the blue regions down here, we'll ignore everything up here. You get these lighter regions down here. So the shaded regions gives you all of it, excluding just the shock or the host galaxy. And we have the stellar mass versus the star formation rate that we infer for those when we add them all up together. You can see that even if it's only just the region kind of in the bottom left, right, it's still a very massive galaxy. And the star formation rate is still potentially 500 solar masses per year, right? So there's a lot of stuff going on, potentially a lot of this driven by this recent burst. The burst of star formation from the jet is so recent that it can't contribute a huge fraction to the stellar mass. So you can see the star formation rate goes up by a lot, but the stellar mass doesn't increase hugely if we say that it's all from induced star formation. But this is photometry, and photometry is very difficult to get detailed constraints on. And this is where a program led by a former PhD student from Leiden, now a postdoc at Oxford, Ayush Saxena, proposed in cycle 1 of James Webb to get resolved near-infrared spectroscopy using the near-spec integral field unit. So here now we have your image, but in each of these pixels we have high-resolution JWST spectroscopy that spans all the way from about 1.5 microns up to 4.5, 5 microns. So spanning the full rest-time optical of this source. And again, it's a very complicated plot. It's a very rich data set, so I can't go into too much detail. But one of the early conclusions was that actually what we thought from photometry was wrong, right? The velocity structure that we can see, and this is a very broad line emission. So this is, like I mentioned, this is high resolution spectroscopy. So all of the broadening you see here is because of the very extended kinematic structure. And so therefore we're confident that actually the emission lines are being driven by these, possibly these kind of winds and kind of outflowing medium that's been photoionized by the AGN. But a very complex and very kind of difficult to interpret structure as you go out around the radio jet. So there's a gradient. So as you move along away from the galaxy. The velocity of the gas is shifting, but there's also, you can see the kind of variation in the velocity structure. There's lots of complex things going on. So it's maybe a more difficult picture than we had before, but it is at least demonstrating that we can start now with James Webb to put really detailed constraints on what's going on in these populations and how the jet is interacting with the galaxy. So another paper that used the same data set by Namrata Roy, who is a postdoc at Space Telescope in the US. If we took the idea that this is an outflow that we're seeing in the near-infrared spectroscopy, we have access to lots of detailed diagnostics that let us measure things like the density of the gas alongside the ionization state. You can start to build up a picture of how much mass is outflowing, and you can see that peaks. There's a kind of red, highest mass outflow is in this region over here, with other regions down here, kind of outflowing gas along the line of the radio jet, but also still a lot of ionized gas around the host galaxy itself. We can start to measure things like the power of the jet, but also the outflow rates in total, that tell us that we're putting this source is extreme in terms of its overall AGM power, but it's also putting out a lot of matter back into the ISM, linking back to what I talked before about the ability to use radio galaxies as probes of this feedback, right? We can start to actually now look at feedback when it was first happening, measure how much energy was being put into the galaxies, how far and how fast the metals and things were being moved around, to look at the chemical enrichment history of galaxies. So this is all very powerful, and I'll skip over this result for now. But this is telling us, right, that we can find some of these sources that in their radio data, like they're there to be found. And if we can find them and follow them up with telescopes like James Webb, we can learn a lot about the galaxy, the interaction that's going on between the jet. But this is quite limited still. So there are the samples I talked about before of these high-energy radio galaxies where it's not a quasar, it's more obscured AGN. They're in their tens to hundreds of sources at redshift 2 and above, and only a handful really known above redshift 5. And another really difficult factor is that the samples are very heterogeneous. So these have been picked by different radio surveys, different optical criteria, different follow-up instruments. And you can see this is work from Ayush Saxena when he was during his PhD in Leiden, where we found a big sample of these. But you can see that all these different surveys using slightly different radio telescopes, different follow-up, make it means it's really difficult to actually learn anything. So even if we fully understood everything that was going on with TNJ 1338, it's such an extreme and a weird and rare object that we can't really interpret that in terms of models of galaxy evolution because it's so extreme. And actually our ability to kind of do that is limited by having homogeneous samples where we understand the selection functions. So demonstrated these surveys are out there, or these galaxies are out there, and if we find them properly, we can do a lot of science with them. But crucially, we need to have representative, so a large range of parameter space, so different jet powers, different stellar masses across redshift range, but with a homogeneous selection function that we can start to do quantitative science on. So this is what leads me to my final section now, just on where we can go in future. So it's relatively short, this section, but this is where Weave comes in. So Weave is an optical instrument. So it's the WHT Enhanced Area Velocity Explorer. So it's a multi-object optical spectrograph being commissioned on the William Herschel telescope. So it's a 4.2 meter telescope. And this instrument has 1,000 optical fibers that cover the full optical wavelength range, plus placeable integral field unit modes. And it has high spectral resolution. So in its low resolution mode, it has a spectral resolution of 5 to 6,000, which is 2 to 3 times kind of SDSS as a comparison. But it also has these very high resolution modes for stellar spectroscopy. So once it's finished commissioning, it's going to be doing a suite of surveys. And so I'll just, hopefully the video works. It might be a little bit 1P, the power of this instrument is these 9,000 fibers are placeable by a robot. So there's 2 of these robots. This is just one of them working at the moment. You can configure these very flexibly and build up 1,000 targets on your field of view. Each of these is a small prism that's attached to a magnet that captures the light and then translates it down the optical fibers. These are on retractors in 3 different layers. And you can basically do infinitely flexible configurations. And while the robots are building one configuration, the telescope observes another set. When you've finished observing, the instrument kind of rotates and the robot starts to make the next configuration while the one that's just done starts getting observed. So the idea is that we can be very efficient and get huge numbers of spectra for these things. So there was some early data that was taken with the integral field unit mode a couple of years ago that demonstrated the power of this instrument. And this is Stefan's quintet. It's been well studied, obviously, over many years, picking out a few examples. So this was as far back as December 2022. So it's made it look like we would have survey data by now, but unfortunately there were alignment issues in the optical spectrograph that were difficult for them to identify. But as of this month, those are basically solved. So we're expecting to kind of restart where we were in terms of this the optical surveys. Once it does start, and this is where I think the fun should come in, we have this big survey. So we have Weave LOFAR, which does what the name suggests. It combines Weave with lots of LOFAR selected sources. And this is led primarily by Dan Smith, University of Hertfordshire, but I'm the deputy science team lead for this survey. And the idea is to follow up 1 million radio selected sources across 3 different tiers. So targeting basically only the brightest sources over 6,500 square degrees. And this will be about 8 millijansky at 150 megahertz in terms of the flux cut. A mid-tier going down to about 0.8 to 1 millijansky sources and brighter, but over a smaller area. And in the deep fields, we're going to basically put a fiber on every single radio source that we can try and cover, regardless of how faint it is. So down to tens of microjanskys. And the idea is that across these three tiers of survey, we'll have near 100% completeness up to redshift 1, but also lots of high redshift galaxies detected above that. And we don't require an optical detection. We can take a blind radio detection that is compact in LOFAR and put the fiber directly on the source and detect that Lyman alpha emission that has been bright in these other radio sources out to kind of redshift 6.6 potentially, without having to have got a photometric redshift, without relying on there being kind of robust optical data. But more generally, the survey goals are very broad, right? We can get source classification, so separate star formation and AGN, accretion mode, but also look at the kinematics. So showed there, right, the detailed interaction between the jet and the galaxy. This shows up as asymmetric line profiles, outflows that we can measure in the kinematics. With Weave LOFAR, we can't do it on a spatial scale, but we can do this with huge statistics, and this is going to give us enormously powerful data set to work with. And I'm conscious that I'm running out of time, so I'll just kind of reiterate, bringing this back to kind of the initial goals I talked about. Although we're mainly going to get most of our targets with Weave LOFAR at redshift 1 and below, the parameter space that's being probed by the different tiers of Weave LOFAR, the wide tier gives us our most extreme kind of radio sources like TNJ 1338, but all the way down to these much more normal, kind of more regular, kind of lower power radio sources that are probed in these deep fields. So this is just the number density we're being probed, and the lower limit here is the volume that the different survey tier will do. So you can see, across the Weave LOFAR deep to wide, we can probe a wide range of parameter space. And the idea here is that even within the first 6 months to a year, we should have 100 times improvement in the number of samples, but with that uniform selection where they're all from the same survey, they're all followed up with exactly the same instrument, and we can start to understand really the full populations and go back with James Webb to understand, get more about the galaxies, understand what's going on. So I think I'll skip that just to kind of illustrate the parameter space, maybe for the for people that might be interested. This is just a 4-meter telescope, so we're not going to see all of them, but this is simulations that have been done by Anik, whose work I showed earlier. And this is the luminosity in the Lyman alpha emission, so the line we'd be looking for on the optical spectra. And you can see that above a certain threshold, this is redshift 5, right? It's a function of kind of signal to noise in the measurement. Basically, anything above this kind of particular radio power, going backwards. Anything brighter than 10 to the 43, right? The recovery fraction is near 100%. And if you look at where this lies in the population, we can see that we're not going to detect all of these sources. But we will detect a very nice cross section that's going to be really highly complementary to these other data sets. And finally, just to kind of tie that into other data sets, all of these fields will be sitting within the Euclid wide area survey, right? So we're going to have about 200,000 of these that will have deep near infrared photometry. So we'll have spectra, we'll have photometry, we'll have the radio, and we can really start to do really robust, really complete studies of these populations all the way up to redshift 7 in a way that was just previously impossible, to start bringing this together and answering that question of how and when did kind of supermassive black holes form, but with a complete sample that's very complementary to the optical ones. But also being able to look then at the host galaxy, because we're not blinded by the optical quasar emission, actually start to understand what those supermassive black holes are doing to their galaxies, how they're interacting through feedback, and building up this really complete picture. So I think I've used up my time. So I'll just leave the summary there. And yeah, happy to take any questions. Thank you very much for your time.
Oh, thank you very much, Kenneth. That's a very impressive talk. And it's also good to see the different components of it, like things done with all the different instruments. I'll open the floor for questions. And I see Catherine has got her hand up. Catherine, please.
Oh, thanks for the nice talk. I think I got that 85% of the sources in lots are identified. So could you have a guess at what the other 15% are?
So that's what I think are these things, right? So 85% is things with an optical ID. And generally that means that they're brighter in the optical continuum when we get a photo Z, and most of them are kind of low redshift. There's some quasars, which is the ones that Anik found, but I think the things that are too faint to be an optical continuum but are in radio are all these radio populations above redshift 2, which we can see in deep fields like Cosmos or the LOFAR ones with deep near infrared, but just are too red and too faint to see in radio. And that's why we have this idea of using Weave LOFAR, where we don't require it to have an optical ID. We can just put the fiber on the radio source, including that 15% with no optical ID. And for many of them, we won't detect anything, but for some fraction, like we should still get a Lyman alpha emission where we have a redshift now to go and look with other instruments. So I think the simple answer is it's basically these higher redshift, low luminosity AGN that are just too faint. And again, to kind of bring it back to where did I have it? The Euclid, I think we will see them in Euclid. I think we'll have near 100% will have a Euclid detection, but it might only be in like one near infrared band. So again, the weave is still really important for that.
Thanks. Can I just quickly follow up with that? So the first survey is at a frequency which is about 10 times LOFAR. How did the source populations compare?
So I think the detection fraction of, so specifically for like the higher redshift quasars, you're saying, or in general?
In sort of in general, what will you pick up with LOFAR that you might not so much with in the first? I mean, obviously it's deeper, but just at the different frequencies, some things will be more preferentially selected.
Yeah, exactly. So I think I showed at the beginning, right, the spectral slope kind of empirical relation. There's potential that we're seeing with LOFAR things that are, the kind of older, kind of more jet dominated things. So I guess astrophysically, one of the things that LOFAR sees that FIRST doesn't is the much more extended jet structure, and that's partly because it's the lower frequency, so the lower energy electrons, but also the low surface brightness improvements of LOFAR versus FIRST. And I guess obviously these are things that Meerkat would detect because it has that better surface brightness sensitivity as well. So I think we're seeing more extended jet structures, but we are also seeing potentially these things that have got the steeper spectral slope that are significantly fainter than FIRST. And then on the more kind of star formation side, I mean, a lot of the deep field science is driven by not the radio AGN themselves, but we're actually just looking at the star formation, and that stuff that really over these areas you can only do with LOFAR FIRST just can't probe that star formation, I think.
Yeah. Any other question? Ken, I wanted to ask you why, is there a reason you haven't looked at the high Z radio galaxy where you are suspecting an outflow? Why haven't you looked at it in the radio, for example, to see if you find neutral hydrogen with which you could measure whether this is really an outflow or not?
Good question. So for some of these we have. So
yeah.
For TNJ, however, Ayush applied for ALMA time, but was not successful. So I think it's certainly something we would want to do, particularly once we realize the full extent of that kind of outflow. At lower redshift, so I showed before, like spiderweb, that's been studied in detail with ALMA because there's this clear reservoir of cold molecular gas and outflows. I think, yeah, you're right. Yeah, cold molecular gas from ALMA would be fantastic for a lot of these. Yeah. I think with this source particularly, we just didn't really understand the full scale of it because it was just, I don't know, there was some structure. It wasn't quite clear what was going on, and until you see the scale of the outflow in the optical, well, the restaurant optical, it was we just didn't know for sure. But I think that's certainly one of the things we want to do long term. To the downside for Weave LOFAR is that it's northern hemisphere, so it's going to be difficult to do that with ALMA. But obviously, Meerkat deep fields, wide area Meerkat surveys as well, plus Foremost, for example, might pick out some of these things that we can go back to in future as well.
Yeah, cool. With ALMA, you should be able to pick up also CO, but how would you estimate the expected fluxes to convince the scientific and technical committee to grant time?
Yeah, exactly. I think I suppose, well, there's some, we have the benefit of some information about, the metallicity and the density of the gas from the like sulfur 2 lines and things. I can't remember what was in the proposal for ALMA, and there's certainly no reason why we couldn't get time with a bigger sample. But if I was on the TAC, my question always is this question I raised, right, is these objects are fascinating, but they are just so extreme and so weird that if we find an outflow in a different form, like, are we still any closer to actually understanding what that does for galaxy feedback as a whole versus some other more kind of sensible population? That I honestly don't know, but I think it would be great if we could get that cold gas.
Yeah, it's just you probably do need some reasonable estimation of how much time you will need on the telescope to get a decent detection to measure the scales of the outflow. But that's quite interesting. Any other questions from the floor? I saw a hand before. I don't know if that question. Eddie. Eddie, you can unmute. Go ahead. If you're speaking, Eddie Dios, I cannot hear you, at least from my end. The other option for you, Eddie, if you can hear me, is to type your question. Maybe we can wait for you to type while we ask if there's anyone else. Any other question? I didn't see the timeline of the Weave project.
Yeah, so that's the time is always shifting. So I think we're expecting now science verification to take place this summer. But we've been in this process. If you asked me 2 years ago, I would have said, oh, it's 2 months away. And then they find some issue. I mean, fingers crossed, touch wood, we should be out of the woods when it comes to the we should be sorted with the spectrograph now. They understand it a lot better. They fix the issues. Everything is within spec and matching the resolution, the sensitivity we expect. So we would expect the surveys to start by autumn this year, certainly by the end of this year. And the goal is for that to be a 5-year survey. There's some political questions about the surveys and how long they'll last, because the observatory is on a 10-year agreement, and that 10-year agreement runs out in 2027, 2028. And obviously it's now had several years without its main telescope working, and whether the UK and the Dutch and the Spanish governments want to spend money again, we have to prove in the first year that we can get good science and it's good value for money. I think once we're up and running, it should be good. But yeah, I think hopefully at least 2 to 3 years of survey at a minimum, but 5 years and longer. For Weave LOFAR, even 2 years would be fantastic, because we're so unique in that selection. But hopefully sometime at the end of this year, there will be public data releases. I think a year to 18 months after each kind of the survey starts, it will be fully public. That will include all the reduced data products, all the raw data, value-added data, and things like that can be used. But there's just a period of a year and a bit of proprietary time. So this will all be public and available for people to do science. And there's more science than we can do with that data when it comes than we have time or ideas. So please get in touch if you have ideas and have questions about certain things you might want to work on. About the statistics and things and how you might be able to get involved. Please, do get in touch.
Oh, cool. Thanks. Okay, Eddie, if you're not able to ask your question now, there is an option to send it via email through Willis to Kenneth, and I'm sure he will be happy to respond. Okay, good. So I think we can draw the curtain here. Thank you very much, Kenneth. That's an awesome talk, and hopefully in the next 1 year. Oh, I see Kevin raised hand. Oh, I see lots of people hands popping up.
Sorry, that was an accident. I was I was going to do a reaction of applause, but now that I'm on, thank you so much for a very interesting talk indeed.
Yeah, you're welcome. Thank you very much for inviting me. Yeah, it's a pleasure.
Yeah, we'll definitely be in touch in another year to find out how the Weave is going and the data coming out of it for various science that we do. Cool. All right. No, thank you very much. And
thank you,
have
everyone.
a good day, everyone. Enjoy the holiday and see you all next week.
Happy Easter to everyone. Thank you.
Thanks. Bye-bye.